Awesome. It is the top of the hour, so welcome everyone. My name is Courtney Dean. I'm the program director for NeuroMatch. It's wonderful to have you all here for our Impact Scholars seminar presentation. So the Impact Scholars program is kind of an extension to the research opportunity through our academies. So the scholars here have been able to do an additional 6 months of research as a team supported by a mentor, which is really great. Today we have 3 teams that will be sharing their work. So we will go ahead and get started with our first presentation, and then it will be followed by about 5 minutes of questions. So whether you're with a different team, a mentor, a community member, please feel free to jump in and ask some great questions. So with that, G Stringers, I'll hand it over to you to go first, and you're welcome to share slides, share your screen, and you can jump right in.
Okay, thank you. I'm going to share my screen. Can you see well?
Yep, that looks good.
Okay. Okay, then, welcome everyone. We are the G Stringers, and let us start with the questions. Static variables tell us where we are, but what if the brain cares more about where we are going? And in this story, we ask, do V1 neurons encode not just behavioral states, but their rate of change? Let's find out. Population level activity in the mouse brain, particularly in visual cortex, is closely linked to behavioral state variables such as running speed and pupil area. These variables play a significant role in shaping ongoing neural dynamics. And given their strong influence, we propose that it is not only the state itself, but it's also rate of change that carries the meaningful information. We hypothesize that V1 activity not only represents the state variables, but also their temporal derivatives. This could allow V1 system to calibrate responses based on recent history and better anticipate future inputs. We can move on. We use 2 large-scale datasets from Stringer et al. That provide population-level recordings from the mouse V1 during both spontaneous and visual stimulation. It is recorded using 2-photon calcium imaging, and in the spontaneous dataset, it includes recordings from around 20,000 neurons during unstructured behavior, such as running, whisking, and pupil fluctuations, without any external stimuli. And in the evoked dataset, it includes around 10,000 neurons recorded during the presentation of oriented gratings. And we choose these 2 datasets intentionally to test our hypothesis in both simpler internally driven dynamics and externally evoked more complex conditions. Okay, so in this analysis, we explored how neurons encode information about static and rate of change behavioral variables. So a state variable represents the system's current condition, like speed, while a rate of change variable describes its evolution over time, like acceleration. In the spontaneous dataset, we examined static variables like pupil area, pupil position, and speed, and their first temporal derivatives like pupil dilation, pupil velocity, and acceleration. And using UMAP, a nonlinear dimensionality reduction method, we visualized embeddings color-coded by behavioral variables. And the structure you can see in the first latent dimensions indicated that not only state, but also rate of change variables were represented. In the evoked dataset, we analyzed speed, acceleration, and the stimulus variable theta, which is the grating angle. And we derived delta theta, the difference between consecutive gratings, and the logarithm of the ratio delta theta over theta, inspired by the Weber-Fisher laws in psychophysics, which state that the smallest noticeable stimulus change is proportional to the original intensity. We applied dimensionality reduction before correlation and predictive analysis. So we implemented linear methods, including principal component analysis and non-negative matrix factorization with rank estimated via a cross-validated elbow method. And we compared it with nonlinear dimensionality reduction methods like Gaussian mixture model clustering. And the outputs from these methods were called superneurons and were compared to single neuron performances in further future analysis. And to assess significance of correlations, we used a linear shift permutation test that is presented in the schematic that revealed that some neurons encoded state, rate of change, or both. And for instance, in this NMF superneurons 5, it was coupled to acceleration and speed, while superneurons 6 and 21 were encoding only one variable. And some superneurons, like the 19, also correlated with theta, suggesting a mix of behavior-specific and integrative populations. But notably, no correlation were found with delta theta, hinting a possible nonlinear relationship.
So based on the results of the exploratory analysis and the correlation analysis that indicated the relationship between neural activity and both state and rate of change variables, we next asked whether we can use the activity of neurons or superneurons to actually predict what the mouse is doing. So let's say the state variable, or how fast what is doing is changing across time. So it's rate of change variable. So in the first step, we used the linear decoders that allowed us to predict quite well most state and rate of change variables. As an example, in the spontaneous dataset, you can see that we could predict quite well the pupil position in X dimension, as well as its rate of change, pupil velocity in the same dimension. So how fast the pupil were moving in X dimension. And this is quite interesting, as it could be, for example, related to saccades. It could mean that V1 holds some information, tracks down saccadic eye movements. And this is important for things like navigation or decision-making in general for the mouse. However, we were also able to predict other variables related, for example, to the pupil area still, like to the pupil, like pupil area or pupil dilation. And this is also functionally relevant for things like arousal and attention. But we could also predict quite well speed and acceleration. Interestingly, in the evoked scenario, we could still predict both state and rate of change variables. Here we showcase speed and acceleration. This is quite interesting since we have now a more complex task for the V1 to tackle. Not only it still keeps on encoding rate of change variables, but it still holds information about an external stimulus, in this case, the presentation of random gratings. And indeed, we were also able to predict this theta, so the angle of the presented orientations. Notably, we couldn't predict so well the delta theta, which is again this difference between the presented angles. And we will come back to commenting on this a bit later. So a natural question that arose was, what's the neural substrate underlying this computation? So basically, is it the same or different neurons that track down state and rate of change variables? One hypothesis could be that we have highly specialized neurons that track down state or rate of change variables. Or another hypothesis would be that we have mixed selectivity or multifunctional neurons that track down combinations of state and rate of change. Our analysis indicates that mostly the second scenario holds true, as when we identified the most predictive neurons for each variable based on the linear predictors, and we computed the intersection over union for those predictive neurons for each variable. We identified this big population, around 40% of neurons in the middle with this yellowish color, that have mixed encoding properties, as they are predictive for both state, speed, and rate of change, like acceleration. However, they also seem to hold some information about the external stimulus, like the angle. Again, mixed selectivity here is quite important, as it offers some versatility in the network, and it can enhance computational power with the same resources. So overall, we were able to predict state and rate of change variables of self-motion, as well as simple features of angles or of an external stimulus like angles. Despite the fact that we couldn't capture stimulus change so well, like delta theta or log delta theta, we still hypothesized that stimulus change is important for V1 and should somehow, maybe in a different way, be captured by population dynamics. So in the next step, we turned our problem into a classification task, and we were able to predict delta theta. So delta theta, again, is the amount of change between two consecutively shown angles. What we did is we took this delta theta and we beamed it into classes of 30 degrees. Each class now represents how big the change was at each time step. This allowed us, using the activity of neurons before and after that change, to guess how big that change was. Specifically, we could guess better the small changes, 0 to 30 degrees, or quite big, 60 to 90 degrees, indicating that these may be more functionally relevant informations for V1, like small or very big changes. Overall, our analysis indicates that some nonlinearity is embedded within the network, and we went on to understand how that nonlinearity may be further there.
So to investigate the nonlinearity of the decoding of state and rate of change variables from single neuron activity and superneuron neural activity, we use neural networks. The definition of superneurons in this case came from Gaussian mixture model and clustering, where we chose that model because it allows for nonlinear relationships between the clusters and the modalities themselves, which is why we didn't use silhouette score for the decision of the number of components, but rather we used AIC and BIC criterion testing to decide the optimal amount of clusters. And the results that you see here are the reconstructions of the state variable orientation or I-STEAM, and its derivative, the log ratio of orientations coming from superneuron neural activity, because they outperform the linear decoding of these variables from superneuron activity. Additionally, you will see the delta theta reconstruction, which was very poor, especially in comparison to linear decoding, which therefore indicates that there might be prevalent linearities between the association of the specific modality and neural activity. Overall, we found that the decodability of orientations or theta and its derivative, the log ratios of orientations or delta theta over theta, was much better reconstructed by the superneurons rather than single neurons, therefore indicating the importance of population-level neural activity in comparison to single neural activity for the decoding of these variables. And also, these demonstrate strong support for Weber-Fechner's law.
Our study indicates that V1 neurons can act as differentiators, encoding both absolute behavioral states and their change over time. We found that V1 neurons encode self-motion and simple stimulus states, as well as rate of change behavioral variables in a linear way. But when it comes to finer features of stimulus change, they also show nonlinear encoding. Additionally, we observed that subset of neurons specialize in tracking specific aspects of the behavior, whether it's state or its rate of change, while others play a more integrative role, reflecting the mixed encoding. So, such rate of change representations may allow sensor networks to adapt their dynamics based on past states, while also anticipating the future ones. And that brings us to the end of our presentation. Thank you all for attending, and we would like to give a special thanks to everybody for contribution through the process.